So till now we have looked into expansion of solids and liquids. Now we are moving on to expansion of gases. This is more dynamic and complex. Reason being, spacing between the molecules is extreme when it comes to gases, right, compared to liquid and solid. So if I happen to consider that this is solid, this is a liquid, gases are something like this. So it's extreme and the particles move faster, rapidly in pretty much all the direction. So you can't predict per se. The intermolecular attraction is almost negligible. So with all of these three factors, whatever I listed, and we have studied this at the start, very start of this chapter. So all of this put together, it's not an easy thing to deal with. And that's why we study it as a separate chapter, honestly. But here it's an introduction. So because of all of this behavior, gases is more dynamic and less straightforward. And so we don't start off directly with, beta, gamma, and alpha, and so on and so forth. We don't go with the coefficient stuff. So we're not doing that. So this is a no. So when it comes to gases, this is a no. So in place of that, what we have is a proper full-fledged mathematical expression. And that too for an ideal gas. Like how you have ideal fluid, right? Here too, we have ideal gas. And for ideal gas, we have ideal gas equation. And that is nothing but your PV is equal to nRT. So when it comes to the world of gas, this is similar to, as in, is as famous as E is equal to mc square gas. Right? So it's as famous as E is equal to mc square. I hope you guys know about this. So what is PV is equal to nRT? It is your ideal gas equation where P is your pressure, V is your volume, N is your number of moles. I hope you by now you guys notice this. R is gas constant. Oh yeah, you might have studied all of this in chemistry. I have not mapped it. I have to check with the chemistry teachers. And T is the temperature. So to understand this, we won't handle all of this variable at one go. What we do is we fix one of it. What we do is, see, PV is equal to nRT, you have three variables and studying them. So this is a variable, this is a variable, constant, and a variable. So what we do is we fix this and we study, say, volume with respect to temperature or vice versa. So we fix one more thing and study the other two. We fix one more thing and study the other two. That's what we do. So I start off with the simplest one. So this is as per your syllabus flow and textbooks flow and all of that. Everyone does this. So they start off by constant pressure. They'll fix the pressure and look into how volume and temperature relate to each other. So we get this expression dV by V is equal to dt by T. So there's a small derivation. I'll just do that. Actually, let me do that first and then move on. Okay, so I'll erase all of this. It's not needed. So we are looking at derivation of dV by V is equal to dt by T. Now we will, we'll start off over here. So we know that proof. So we know that. So this too is an equation that we'll see how it came into being. P is equal to nRT. So this we are taking it as given per se, So it's like axiom for us as of now. It's not. But we are just taking it as, okay, this is given. This we know of. How it came into being, how did people study this? And how is this formula here? That is a discussion for next chapter. So for now, we're just taking this as given. So remember, P is constant over here. Where here or considering P as a constant value Okay. Then we are differentiating. Differentiate above equation with respect to, say, T. Okay. So what do we end up with? Remember, P is a constant. Derivative of this is temperature dependent. And N into R into derivative of T is 1. dt by dt, right? Then we will just rearrange this a bit. So we want this expression, right? So we have substituting P is equal to N into R into T by V. So if we do that, so we'll end up with NR T by V into dV. So you can see we're almost getting the answer. Oh yeah, by the way, dt I'm transposing to the right hand side. So I'm substituting and doing all of that. So NR gets cancelled. A bit of rearrangement. And we get this. Yeah. That's your final answer. I mean, this particular thing. But what does this actually mean? So it's a simple, straightforward, commonsensical stuff. See, all this is very much, we can verify it just with a cooker, literally. Just stand in the kitchen and just watch the cooker or just watch boiling water, right? Even if you're taking bath with hot water, which I don't advise, but or if you are, then yeah, cold water is what I advise. So if you're wanting, at least room temperature. So what does this expression mean? If the temperature increases by a certain percentage, the volume also increases by the same percentage. That's it, as simple as that. As long as the pressure does not change. Okay, so you can learn about gases in many ways, and this is commonsensical. If you think about it, this makes sense. If I increase the temperature, if I have to fix the pressure, so I have to increase the volume. Again, think of a cooker whose volume is fixed. So what happens to pressure? It increases. If you take a cooker, if you heat it, right, with water in it, of course, closed and everything, what happens? Since the volume is fixed, the pressure has to increase. So we are not letting the pressure increase. So we are so to do that, what should we do? We should keep increasing the volume. It keeps the cylinder, you can imagine, keeps getting bigger and bigger. Of course, it's not possible per se, but you can imagine that. If I keep doing that, then yeah, we can get that relation. So we have coefficient of cubical expansion. So yeah, I know that I told we won't be using this per se, but we are deriving it with the mathematical expression. We are not directly jumping onto it. We are not telling, just take this value and you have the material. This given material for that, this is the value. It's not that. It's not as simple as that. So we are deriving it out. So mathematically, it's defined as your coefficient of cubical expansion is 1 by V dV by dt. So for an ideal gas, this expression becomes 1 by T. Okay, so for an ideal gas at a constant pressure, beta, which is your coefficient of cubical expansion, it is 1 by T. Okay, so let's do this as well. Again, beta is defined to be so. So we are looking at beta now. So beta, which is given by given by, okay, I don't know why am I doing that. Beta is equal to 1 by V dV by dt. So, but where is that we have seen dV by dt? So over here, where is it? dV by dt is V by T, right? So we actually have to, technically we have to do this. That is, we should write with, we know that PV is equal to nRT for constant pressure. So we have dV by dt is equal to nR wait, where is it? dV by dt is nr by p, which is 1 by t. If I rearrange this expression, I'll get 1 by t. Okay, so when I substitute, wait, v by t, my bad, sorry, v by t. If I want this expression, if I rearrange this, or let me not do that actually. So on differentiating, we get this, is it not? So from 1, what we have is nr by p is equal to v by t. Therefore, dv by dt is equal to v by t, and beta is equal to 1 by v into v by t. So v and v gets cancelled. So we have 1 by t. And that's that. So ideal gas at a constant pressure is this. Okay, so ideal gas at a constant pressure has a coefficient of cubical expansion. It's a constant, of course. So this, it's given by this particular value. Okay, just keep, constant for a given temperature. So yeah, it would be so. So what does this mean? What does this beta mean? Beta tells you how sensitive the volume of gas is to temperature change. Okay, so beta tells you how sensitive the volume of a gas, any given gas, X gas, is to temperature change. So we have more interpretation in the next slide here. See, beta and T has an inverse relationship. So the graph is so. Okay, so the graph is so. So basically for lower temperature, right, volume expansion coefficient of ideal gas is inversely proportional to absolute temperature. So absolute temperature is one more word, one more phrasing that we'll be introducing in this section. So I'll explain what is absolute temperature. So basically this is what we need to observe. At higher temperature, gas expansion is less for each 1 degree raise. So this is a bunch of higher temperature. So if I increase the temperature by 1 degree, the volume expansion of the gases in terms of percentage per se is much lesser compared to over here. See guys, it's common sense again. If you have a gas, right, near absolute zero and all of that, so say it's very cold. So when you expand it, the next second it might be so, next microsecond, and further it might be so. But once it's reached, the maximum, then the rate at which it keeps expanding is lesser. So if you people who are into economics, you guys can understand GDP, right? The percentage, the rate at which a country's GDP grows. If the base rate is pretty high, then even 1 or 2% increase, it's a huge number. Okay, let me put it this way. If you have 1000, right, 1% increase over here in comparison to say 20, 10% increase over here. Which increases more? It's a simple question. I want 1% increase, or let me tell you, okay, let me put it this way. 1% of 1000, is it more than 10% of 20? Right? 1% of 1000. So that's what this graph is telling. Okay. So, not exactly that, but that is the basic funda. So once you already have reached certain volume, and further addition of 1% also is a pretty significant increase. Mathematically, it will end up looking like this. So at lower temperature, gas expands more for each degree rise. So mathematically, it looks like that, but yeah. Okay, so it's a very new thing. So this is just an introduction. All of this will be dealt in detail in another chapter. So we're looking at expansion of gases. So expansion of gas is very complex. So we go with a mathematical expression, P is equal to nRT. We take it as given. So how did it come into picture? That is a study for another topic, another chapter altogether. So we start off by fixing the pressure. Pressure is fixed, as in it's constant. So we're looking at how temperature influences volume. And so we ended up with quite a few expressions. So first we have dV by V is equal to dt by T. So it's common sense, as in when I increase the temperature, the rate at which I'm increasing this, the volume also increases at the same rate. Next, we looked at something called as coefficient of cubical expansion. So this is a constant. So for ideal gas, we have beta is equal to 1 by T. Again, what is an ideal gas? That also, you guys can, for now, you can imagine what it might be. So that definition, all of those will be added eventually. So we're just interpreting what is beta, what is its relationship with 1 by T. When you plot it, it looks like this. So basically what it's telling is, if you have the gas at lower temperature, if you start increasing it, suddenly you see that the gas has expanded a huge amount. But if you already have reached certain good temperature, increasing post that value in terms of percentage increase, right? The next value of volume increase might not be that significant. It's because of all of this fact, you already have achieved a big number. 1% increase over there is also pretty significant, right? So here at lower temperature, say this is the volume of the gas. So even a 10% increase will not be a big number. But if you already reached a big number, then even 1% increase is a significantly huge. Okay, again, please understand it this way. If not, mathematically, I could have just told the formula. But I'm trying to make you guys push in something new, to approach it new, to think in a new manner. This is how you have to think as a engineer, as a scientist, right? So logical skills, actually, not only we set of people, but everyone should think logically. Okay, yeah. Instead of copying all of this, everything is needed. I'm showing the derivation.